Alright, this is Mr. Gillum, and today we're going to learn about some isosceles triangles. Alright, and I'm sure you know what an isosceles triangle is from previous math classes, but if you don't remember, we're going to go over it. And we're going to learn a theorem about isosceles triangles, and it's kind of going to go right hand in hand with what we've been talking about. Alright, first things first, an isosceles triangle is a triangle that has two equal side lengths. Alright, two equal side lengths. That's the only qualification. It has to have two sides of equal length. Two congruent sides are called the legs, and the angle between the legs is called the vertex angle. So I want to go ahead and label this diagram here so we're all clear when I'm using this vocabulary what I'm talking about. The two sides right here, these little dash sides, those are the legs. And the included angle between the legs is called the vertex. Alright, side opposite the vertex is called the base. So this guy's the base right here. Alright. The two angles formed by the base and the congruent sides are called the base angles. So each of these guys right here is called a base angle. So we know what the vocab is here. We got the vertex, which is the included angle between the two congruent side lengths. We have the base angles, which are the angles made between the legs and the base. Okay? So that's all you really need to know about an isosceles triangle and how it works, and those are the main vocabulary terms that I want you to be familiar with. Let's take a look at the next little slide here. It has a theorem on it, and the theorem is called the isosceles triangle theorem. So we're going to talk about the theorem and its converse. Now the theorem basically has to do with all these relationships we've been learning about the angles and their opposite sides, things like that. Okay. In this case it says the two sides of a triangle are congruent, then the opposite angles are also congruent. So as you can see here, if I have these two, this is an isosceles triangle. This would actually be the base. These are the legs, the two congruent parts. This is the vertex. And then these would be the base angles. And what it's saying is, if you have your two congruent sides, opposite of them are two congruent angles. Okay? So if the sides are congruent, then the angles opposite are congruent as well. Alright? It would make sense because we know that in a triangle, the longest side is across from the biggest angle, the second longest across from the second biggest angle, and the third longest obviously across from the smaller angle. So we've talked about this relationship before, but with an isosceles triangle specifically, if you have two of the same exact side lengths, then you have two of the exact same angle. Alright, which would make sense. Well, the converse basically says the other thing. It says if you have two angles that are exactly equal, then the opposite sides are equal as well. So if angle 1 and angle 2 are congruent, these base angles are congruent, then that means that these sides are congruent, and that is the converse. Okay, if you have the angles, then you know the sides are congruent. That's the converse of the isosceles triangle theorem. All right, so the theorem itself. The theorem itself starts with the sides, and the converse starts with the angles. Oops, went the wrong way. Starts with the angles. All right. So that's the isosceles triangle theorem and its converse. And so let's go ahead and put it to the test here on a theorem. I guess, but before we do that, what we can do is let's just make sure that we understand it. So if I were trying to name two unmarked congruent angles, okay, I couldn't say angle ADC. These are marked. They're already marked. I already know they're congruent. So I'm looking for another pair of congruent angles. What I see here is I see these markings right here. And it looks like a pyramid. So it's kind of like deceiving almost the way it's drawn. But if these two sides are congruent, then I know that the angles opposite of them are congruent. So I could say that this angle and this angle are congruent as well. So I'm going to say angle ACB is congruent to angle ABC. All right, so that's through my isosceles triangle theorem. All right, now the converse is going to help me to find two unmarked congruent sides. I'm going to write this down because I want to make sure that we know the difference between the theorem and its converse. That's the isosceles triangle theorem. It's telling me which angles are congruent. I'm looking for two congruent sides that are unmarked. I already know these are congruent, so I can't count those. I'm looking, since I know that these angles are congruent, I know that their sides opposite must be congruent. So I could say that AD is congruent to AC. All right, those two are congruent, and so and they're unmarked. So now I know that these two are congruent as well. And that is when you're given the angles and you know that the sides are congruent, that's the converse of the isosceles triangle theorem. Okay. All right, so that's what the theorem's saying, and so I'm going to try to incorporate that in some of our proofs. And so here's an example of one. Oh, what? Do another diagram first, I guess. It says name two unmarked congruent angles. Once again, if I'm looking for the congruent angles, that tells me I'm using the actual theorem itself. I know that these two sides are congruent, and if they're part of this big triangle right here, then I know that the opposite angles must be congruent as well. So in this case, I know that angle FGJ must be congruent to angle FJG, and that's through the isosceles triangle theorem. It tells me if I have sides, then I know the angles must be congruent. And then if I'm looking for unmarked congruent sides, well, they give me this pair of congruent angles, and this, let's just change colors here so we can see. In this triangle, this big triangle right here, here's two congruent angles. The sides opposite of them is what the converse of the theorem says, must be equal. So I know that GH and JH must be congruent as well. All right, so that's the converse of the isosceles triangles theorem. All right, so pretty basic, I guess. I don't know. Let's try it in a proof and just see how it works out here. Let's see here. Now, there's a reason I covered up the proof this time, because I don't want you to be confused about all this. Unfortunately, this is the best I could do as far as the diagram goes for the given problem here. Honestly, they're not going to give you some of the information that you see on the diagram. Okay, they're just going to give you a triangle, L, M, and P. And it's just going to be very plain. It's just going to be a triangle, and that's it. That's all they're going to say. All right, and they're going to give you a little given information. They're going to tell you that LM and LP are congruent. Okay, they'll tell you that. But they aren't going to give you all this other stuff. Okay, they're just going to give you this diagram right here. And what you're going to be responsible to do is, you're going to first of all, you're going to put a midpoint on here. Okay, and you're going to see why that's important here in a second. We're just going to call it midpoint N. All right, midpoint N. And we're allowed to do that. We can put points on there, and there's an infinite many points on the segment, so that's okay. So I'm just going to put that midpoint on there, and every segment has exactly one midpoint. So we're going to just let that midpoint be in. We're going to actually physically put that on there and label it ourselves. Okay. We're also going to draw an auxiliary line. Okay, and that's this guy right here. It's called an auxiliary line. And it's going to help us to make another additional triangle, okay, from our diagram. So we're going to actually put an auxiliary line in there as well. And we're going to connect L to N through that auxiliary line. Okay, so I'm making a new segment LN. All right, and basically this goes way back to like when we first had those postulates, and I was like, okay, write 4 out of the 8 on your paper. Okay, two points make a line, and so we're able to draw an auxiliary line in there, no problem. I haven't broken any rules. It's almost like a definition, kind of 2 points determine a line. Now, if this is truly the midpoint, which I have stated that it is, then I know for sure that MN is congruent to PN. Okay, so I'm going to go ahead and label that, and that's the midpoint theorem. It says if you have the midpoint, then each part of the segment on either side of the midpoint is going to be the same distance. All right, and we go on. It says ln is congruent to ln. Well, obviously we know this. And so what we're doing is actually we're moving towards having these little triangles, I'm going to highlight the two triangles I mean when I say little triangles. We're moving towards proving that LMN and LPN are congruent through the side, 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 because apparently we have the given. We have, through our auxiliary line, guaranteed that these are congruent, and they share this side right here. So through those three things, sorry, I guess I didn't write the given down yet. Throw in the given there. I know that those triangles are congruent, okay, through the side, side, side. And if those triangles are congruent, then I know that angle M must equal angle P through the corresponding parts of congruent triangles. Or sorry, corresponding parts of congruent triangles are congruent. That's what CPCTC means. And we can write that down. Again, C, corresponding, P, parts, C, congruent, T, triangles are congruent. Corresponding parts of congruent triangles are congruent. All right. Guess I should put the word of in there. All right. And so this could be a little challenging because we actually had to do some of the work to put the auxiliary line in and label a point N and all that. So just keep in mind, if you're given a very plain diagram, you might have to do some auxiliary lines just to help with the process. Now notice I didn't have to make this angle 90-degree angle. That didn't matter. Had nothing to do with it. Because I was proving those two little triangles make the big triangle, and eventually these angles of these two triangles would be congruent because they are equal triangles, congruent triangles. So remember, all our proofs from this chapter are based around triangles. So if you don't see enough triangles or you can't prove two triangles congruent, then you're probably not doing something right. You want to make sure the triangles are congruent. Make two triangles if you don't have two triangles, and then try to find that their corresponding parts, once you've proven them congruent, their corresponding parts should also be congruent. So that's it for today. Just to see if everyone was listening to the end, I want you to put a little smiley face in the top right-hand corner of your paper. That's it.